Welcome to this video. Today we're talking about Softpick, no attention sink, no massive activations with Rectified Softmax. This paper was published 5 days ago by the Mohammed bin Zayed University of Artificial Intelligence, and the overall idea of this paper is to replace the Softmax function in the attention formula with a so-called Softpick function, and this should bring some benefits with it. So let's just find out what the benefits are, and let's just read the abstract therefrom. We introduce Softpick, a rectified not sum to one drop-in replacement for Softmax in transformer attention mechanism that eliminates attention sink and massive activation. Okay, so if we replace the Softmax function with Softpick, the authors are claiming that it can eliminate attention sink. Okay, so what is attention sink? Attention sink means that our model puts in a sequence of tokens all the attention just to one token, and most of the time that's a begin of sentence token. Okay, so if we have like a begin of sentence token, we have token 1, token 2, token 3, and then we also have one end of sentence token. The model puts all the attention to this begin of sentence token. We actually can see it in this figure already. So if we look at this figure, we see this is the Softmax, the attention map for Softmax at layer 10 had 13, and on the right side we have the Softpick layer at layer 10 had 13. So we're comparing the same layer, same head, but different function for the attention values. One's a Softmax and the other one is a Softpick. And what we can see in the attention maps, so this one is like the attention map, we can see that the model puts all the attention to the first token, so the begin of sentence token, and it's not so good distributed if we compare it to the Softpick layer. Our experiments with 340 million parameter models demonstrate that Softpick maintains performance parity with Softmax on standard benchmarks while achieving 0% sync rate. So if we replace Softmax by Softpick, the attention sync no longer happens, and now they are talking about the kurtosis in the next sentence, and kurtosis measures how our distribution is shaped. So if we have a very high kurtosis, this means that we have a sharp peak and very heavy tails. So we could see it in this picture. So the blue curve has a higher kurtosis, and this one, for example, has lower, and this one even lower kurtosis. And normal distribution have like a kurtosis of 3. And now if we have a very high kurtosis, what we have if we are using Softmax means that we have a lot of outliers and a very peaked or very sharp peak. Okay, and let's maybe look at the formula how we could calculate kurtosis. So it's like this: we have random variable x, and then we have the expectation of our random variable x minus the mean that we calculated before, and we divide by the power 4 of the standard deviation. And so this one would be like the normal standard deviation, but now we are not using power of 2, but we instead use power of 4. So what makes power of 4? So if we have outliers have even more impact to our kurtosis compared if we just use the variance here. Okay, this is why we are using power of 4, and it's just a measurement for our distribution, and this one is just a normalization factor. So let's continue. Models using a Softpick consistently outperform Softmax when quantized, with particular pronounced advantage at lower bit precision. Okay, this is because we have like lower activations, or we eliminate massive activations, and it's hard to represent very high values with just a few bits. So if we are using a lower bit training or using quantization, it's better if we use a Softpick, because then we eliminate a massive activation. That's what the authors are saying here. Our analysis and discussion shows how Softpick has the potential to open new possibilities for quantization, low precision training, sparsity optimization, pruning, and interpretability. So interpretability comes from the sparse attention maps. So if we have sparser attention maps, we could maybe find out how the model puts the attention to all the other keys, and maybe it's more interpretable for us. Okay, you could also check out their code at GitHub. And so let's just jump into the introduction. Okay, we already talked about two disadvantages of Softmax. The first is attention sink, and the other one was that massive activations can occur. And the thing with Softmax is it also has a lot of advantages, and maybe let's look at the advantages of Softmax. And the first is that we have really good gradients, and our gradients are calculated with the Jacobian matrix, because we have a matrix of derivatives, because each value here, if we change the value of 7, it also has an impact on the result of all the other cells of our matrix in this column. Okay, so this is why we have like a Jacobian matrix, and this Jacobian matrix is has a bounded Frobenius norm. Okay, the Frobenius norm is actually the same as the L2 norm, so we could calculate the L2 norm of a vector, and the Frobenius norm is the L2 norm not for a vector but for a matrix. And this brings, so that it's bounded, this helps to have a very good gradient, so we don't have vanishing or exploding gradients, and this helps us for the training stability. The next thing with Softmax is we add like a nonlinear function to it. So if we would just, for example, just sum up all the values and then do like an averaging, we wouldn't have a nonlinearity function, but with Softmax we do have a nonlinearity function, and nonlinearity function makes our model stronger in the representation. Okay. So if we go on here, they are actually just talking again about the begin of sentence token, and that the model can put a lot of attention to the begin of sentence tokens, and this is not helping. And then in the next step they are talking about that the activation, if they are very high, we have problems with lower bit training and quantization. And I would say that's all of the introduction, and we could jump into the background, or maybe already here to part 3 of the paper. We have given a vector called x. X is an n-dimensional vector and corresponds to our raw attention values by calculating the dot product between all the queries and all the keys. And normally then we put the Softmax function on top of those values, but now the authors are introducing the Softpick function, and Softpick is a little different if we compare to Softmax. And in the numerator we can see we have two changes. The first change is that we are subtracting by -1, and the result of it we are putting into a value function. Let's try to understand the change in the numerator. And the overall idea was that it should be possible that one token puts 0 attention to another token in the sequence. Okay, but this was not possible with the Softmax function. And now it's possible with the value function. And why is it possible? So normally we have our exponential function, and the exponential function goes like this, and it's not at the origin. Okay, If we're now subtracting by -1, we are shifting it towards the origin, and now it goes through, so it looks more like this. And yeah, we have now here negative values, and if we now put on top of this the value function, the result of our numerator looks like this. Okay, so if we now have a negative dot product between one query and one key, this means that we have a negative dot product, and this is the result of it, that we get 0 as the attention value between this token for this query and the key, the corresponding token for the key. Okay, so this is why we the authors did the change in the numerator. If we now look at the denominator, we see there we didn't have the value, and this is because if we have our value function, we don't have a gradient here, because the slope of this function is 0 for negative values. And if we're putting here, instead of the absolute value function, also the value function in the denominator, it leads to very bad gradients. I think they're saying it here. So however, this is also a weakness. We experimented with this rectified only softmax and found that it diverged from baseline softmax after a longer training period, and hypothesized that this is caused by heads dying and not being able to recover from outputting only zeros. Okay, so we can see here actually they tried to put also the value function in the denominator, but we have very bad gradients then. So this is the next thing, and this is obvious when we look at the Jacobian of the function. So if we look at the deviation of our function, then we have if we have negative inputs, we do not receive any gradients, because they do not contribute to the output nor the denominator. Okay, so if we have for one xi, if it's a negative, it doesn't have an impact on the denominator and numerator, and so we have a lot of gradients that are 0, and this is a problem for our training. And this is actually why they add the absolute value function on top of it. And now we can see equation number 2. They're just doing some changes to this function, because they want to make it numerically safe. And one step is to add an epsilon that we are not dividing by 0. And the second step they add is just subtracting x by -m, and m is a maximum value inside x, and it's just because if we have pretty high values, for example 1000, and we then calculate the exponential function of it, we have the possibility that we reach infinity, and if we reach infinity, that's not good for our training, so our training actually stops and diverges. So if we have a vector like this, we are just subtracting the maximum value, we're taking the maximum value inside x and subtracting the values with this maximum, and then we are not reaching infinity. Okay, so also very basic, and they just doing it that we have a numerically safe version. And this is how actually the end softpick function looks like, and how is it implemented. So let's continue. We have here one more section about the derivative, and just one interesting thing actually is if we are not having the if we would have the value function, and we have like the possibility that both of those would be 0, and we don't want to do this, we don't want to have this, and this is why we add the absolute value function, or why the authors added the absolute value function into the denominator. To sum it up, let's just have a small view on the experiment and result part. So first of all, they trained llama style transformer with 340 million parameters, and they used 52 billion tokens. If you want to see more about the training configuration or hyperparameters, you can see it in this table here. And I actually just want to show or focus on two figures. One is figure number 3, and here we can see that the quantization results of Softmax versus Softpick, and the quantization results show that the Softpick always outperforms the Softmax, and the reason for it, we already talked about it, that Softpick eliminates massive activation values. So we can see it in this figure here. We can see the activations from layer 1 to layer 24, and we see as we go deeper the activations of our Softmax gets very high. If we compare to the orange line, we can see that the activations are much smaller, and then it's easier to represent a smaller number with a few bits and a very big number. Okay, so I think we can now just jump into the last part, and this is where is it? Yeah, we can see it here. It's called passkey retrieval. So the task is passkey retrieval, and the overall idea is that we have like a sequence, and the sequence length, for example, is 890 tokens long. So we have 890 tokens, and now the task of the model is to retrieve one passkey, so one token from this sequence. And if it gets right, we get a huge, we get a good accuracy. If it's not good at this, we get a not so good accuracy. And we can see that Softmax always outperforms Softpick for this specific task. And the reason for it, we can find out together with the formula, and also the authors are saying here what the reason for this can be. So let's just have a quick view back onto the formula. And the interesting part here now is that if you have a really large sentence and we just want to have attention values for like high attention values for just a few tokens, then this means that for a lot of values the numerator is 0, but the denominator is not 0. So if I have if one token has zero attention to another token, this means that all the other attention values get smaller because the denominator still increases. And if we now have a very long sequence and just a few tokens that we have to put attention to, then this can be a problem, and this is why maybe the passkey retrieval task with Softpick is worse compared to the Softmax. And we can see if we have a higher sequence length, this effect even gets larger. I think we worked through the most important parts of this paper. If you want to read the paper by yourself, you can find the link to the paper in the video description. And yeah, that's it for this video, and I hope we will see us in the next video.